Hi, my name is Christina Quintero, and this is my video lab report for Lab 5, Choose Your Own Adventure. The purpose of this lab is to view the changes in energies in an object being dropped, including drag force and without drag force, essentially combining Labs 2 and 4. A video was taken of a ball being pushed off a ledge. Tracker was then used to extract data from the video, then a code was written to model the motion using Newton's second law and the energy principle. Both the model with and without drag satisfies the energy principle, though the model with drag more accurately models the motion. The principles being used in this lab are Newton's second law and the energy principle. Newton's second law is used to predict the velocity of the object using its mass and the net force. For this experiment, the model without drag will have a net force equal to the force of gravity, and for the model with drag, the net force will be equal to the force of the drag plus the force of gravity. The second principle being used is the energy principle. The system for this experiment is the ball plus the earth. Therefore, delta E equals delta K trans and delta gravity potential. The video was analyzed using Tracker. The calibration stick was set to the height of the dresser, which was 2.058 meters. The origin was set to where the ball was dropped and the ball fell in the negative y direction. The data was then recorded in the table and graph located on the side. The video looks like this. Using this data, the code was initialized. The ball had a mass of 25 grams, and the initial position of the ball was negative 0.006, negative 0.0060 meters, and it had a zero velocity since it started from rest. Other initializations were defining G as 9.8, defining j hat as the positive y direction, and defining b, the proportionality constant, based on the data from Tracker to be 0.005366. The system's energies, translational kinetic energy, and gravitational potential energy were defined at the bottom. The calculation loop was set to run for 0.7 seconds. Here, the force of gravity and the drag force are defined so that F net can be calculated. When the model is run without drag, F drag will be set equal to 0. Next is Newton's second law, so the new velocities can be calculated over time, followed by the position update equation. These lines of code are used to calculate K trans and the gravitational potential energy, along with delta K trans and delta gravitational potential energy, as seen earlier in the energy principle. When we run the code without drag, we see this model. The yellow arrow represents the force of gravity. On the graph, the blue equals the delta K trans, the green equals delta E, and the red equals delta UG. When we run the code using drag, it looks like this. For this graph, the additional blue arrow equals the force of drag. For the energy graph without drag, delta UG and delta K trans are linear. This is because as the ball constantly accelerates due to gravity and no opposing force. As the speed of the object increases, so does the object's translational kinetic energy. Inversely, the change in gravitational potential energy constantly decreases as the object falls to the ground. The energy graph of the model with drag was different. When an object is acted on by the drag force, it eventually reaches a terminal velocity when F grav equals F drag. For this reason, delta K trans can be seen accelerating until the ball begins to reach terminal velocity when the change in delta K trans begins to decrease in magnitude. This is also reflected with the slight upward curve in the delta UG curve due to the ball approaching terminal velocity. In order to determine which model most accurately predicted the motion of the object, the data from Tracker was plotted on a graph. Then the code with and without drag were ran to collect position data for the two. These were then added to the graph. The blue shows the actual, the red shows the model without drag, and the green shows the model with drag. The graph without drag overestimated the distance traveled, which can be seen between the difference of the blue and the red lines. The model with drag had little error in comparison and was determined to be more accurate, as can be seen on the graph. Thank you for watching!